Guess who's back? Back again. No, it's not me. It's not this intro. It's the series on topology, and I'm starting it from scratch. Okay, it's gonna be better this time, I promise. But yeah, it is back. Oh yeah. Okay. Anyway, so today we'll be doing open sets and continuity, both, and we're going to link them together. So first of all, let's look at an intuitive view on continuity. So intuitively, a function is continuous if we can just, like, with one stroke of the pen, that's not a function, but you know what I mean, like we can just draw it with one stroke of the pen. So, for example, that really crappy sine wave, or the graph sine x, is continuous because we can draw it like that, okay? It's continuous everywhere, okay? So a function is continuous at a if, let me write this down. So if x1, x2, x3 and so on converges to a, okay, then that should imply that f of x1, f of x2, f of x3 and so on should converge to f of a, okay? And if this does that for every sequence, then this f is continuous at a. Okay? So of course that will hold for most functions. Let's take a look at a counterexample, a quick counterexample. If we have this function here, which looks like this, okay? So it's the derivative of the absolute value of x. Or in other words, the absolute value of x over x, this function here. Is it continuous at 0? Okay? Well, one sequence which converges to 0 is 1 over n. Or 1, 1/2, 1/3, and so on. Seeing as these are all positive values, then f of 1, f of 1/2, f of 1 over 3, so on. Positive, so it spits out 1. Positive, so it spits out 1. Positive, so it spits out 1, so on. And therefore f of 0 should equal 1, or it should converge to 1. And we have no problems. This function is continuous at 0. Wrong. Hopefully you can already see an easy way to show this is wrong is if we take a look at the sequence negative 1 over n. Again, this converges to this converges to 0, but from the other side, so negative 1 over 2. Hello from the other side. Yeah, negative 1 over 3, so on. This will still go to 0, okay? But because this is negative, we can see this will spit out negative 1, negative 1, negative 1, negative 1, so on. So surely f of 0 should equal negative 1. What? Negative 1 doesn't equal 1. To my knowledge, anyway. Okay? And hence, these two, we're at a contradiction. And therefore, this function is discontinuous at a. Not at a. Sorry. At 0. Okay? And so we kind of have our definition of continuity. If this sequence converges to A, then f of x, f of x1, f of x2, so on, so on, so on, should converge to f of A. Okay? While this is all good, this is fine, it's kind of impractical because we'll have to consider all of the sequences, and that's not nice. So instead of using sequences, why don't we use margin of error? Call it epsilon instead. So, for example, for every input x, the distance between x and A should be less than delta, so margin of error. And that should imply that for some other margin of error, epsilon, f of x minus f of A is less than epsilon, okay? So now continuity becomes a game, and I shall lay down the definition. Okay? We say f is continuous at A if. Okay? The distance between f of x and f of A is less than epsilon whenever the distance between x and A is less than delta for some epsilon greater than 0 and some delta greater than 0. Okay? So it becomes a game. I claim f is continuous. Oh, I have to find some delta such that this is true. Okay? Oh, you picked f of 1 and f of 2. Oh, I have to pick some delta. Okay? Such that 1 is less than delta. Okay? And so on, so on, so on. And now, this is all nice, but this idea of distance here is not so nice, okay? But before I move on, I'll motivate you'll kind of already see, how we can use these open sets, which I'm going to define, to describe continuity, and that's going to be the point of this video. So if we take a look at the distance between x and A being less than delta, we can rewrite this, okay? This implies, well, the distance between x and A is equal to the distance between A and x, okay? So this implies that A is less than delta plus x. Oh, sorry. What is wrong with me today? Okay. This is not what we wanted. We do want to write it like this. My bad. Okay? This implies that x is less than delta plus A, but whoops. Oh my gosh. Simple algebra, Gregor, simple algebra. Okay. Or, instead of adding A on both sides, okay, what if we add x on both sides and subtract delta, leaving us with A minus delta is less than x is less than delta plus A. Okay? Which is the precise definition of the open interval a minus delta, a plus delta. Okay? And I'll keep this idea in mind for later on when I prove something. Okay. But for now, that was just a little detour after our discussion about continuity. For now, consider just the real line. Okay? What pen? I don't know. I'll use purple. I haven't used it today, I don't think. So if we have the real line. Okay? And if we have an open interval, well, what main property does it have? It has the property that for every x I pick in it, we can always construct some open interval around x of some radius, let's call it epsilon. Okay? That's good. So this point is inside of this, let me make this bigger. Let me make our open interval bigger. Okay, if we pick this x here, it's somewhat inside. It can be close to the boundary, so for example here. But as soon as it gets on the boundary, this becomes a closed interval. Okay? And that's the main property of an open interval. Right? So why don't we just generalize this to open sets? Okay? With our example of the open interval. And we'll define the open set. We say S, contained in the real numbers, is open if for every x in S, okay, for example this x, there exists some delta sub x greater than 0. Okay, that's going to turn out to be this radius here, such that, okay, the open interval between, well, what's it between? It's between x minus a delta sub x and x plus delta sub x, okay? Hopefully you can see that here. So if we go this way, then it will be x minus delta sub x, and if we go that way, it will be x plus delta sub x. And remember, this has to be completely contained inside of S. Okay, so if we think back to that open interval we had, that open interval had to be completely inside. Okay? So let's just take a quick look at an example. For example, the open interval between 0 and 2. Is this open? Well, yes. Okay? First consider x being less than or equal to 1. Okay? Then we can choose delta sub x in this definition to just equal x. Okay, that's pretty simple, because then we're left with the open interval about x minus x, 0, and x plus x is 2x, which is completely contained inside of the open interval between 0 and 2 because of this. Okay, as x is less than or equal to 1. Now, consider when x being greater than or equal to 1. Now, to take a little bit more care. We have to choose delta x to equal 2 minus x. Okay? Then we're left with the open interval between x minus 2 minus x minus 2, and then minus minus becomes plus x, or 2x minus 2, 2x plus 2 minus x. Well, the x and the minus x will cancel, leaving us with just this, which is again completely contained inside this open interval, as x is indeed greater than or equal to 1. Okay? That was just a little example. And just a quick side note, okay, you might be wondering what a closed set is. It's just a closed set is one in which S is a closed set if the complement of S is open. So the stuff that's not in S, so if we take our example of the real line, if S contains its boundaries, then the stuff that's not in S will not contain those boundaries. Okay? It's always going to be open. Okay? It's probably going to be the union of two open sets, because if the complement were to contain the boundary, then that would mean that the boundary is not in the set S, which would mean it's open. So for the set to be closed, the complement must be open. However, we're not going to study closed sets today. That's just a side note, in case you're wondering. Instead, we're just going to prove one little result about open sets. Then we'll do a brief definition of something which we need to know before the main point of the video, which is to characterize continuity in terms of open sets. Okay? So, first of all, we'll do our first little theorem, which is let S sub I be a collection of open sets. Okay, now I ask, what if I take the union of all of those open sets? But then, the union, let that be a collection, let Si indexed by I in some set I, just some set arbitrary set I, okay? Okay, be a collection of open sets. Okay, then the union over all of these open sets is open. Okay? So if we take a bunch of open sets, doesn't matter whether it's infinite or finite amount, okay? And we union them all together, they'll still be open. Why? Well, if X is in some S sub I, okay? Remember that S sub I, all of these are open. So that would imply that there exists some delta greater than 0 such that the open interval between x minus delta and x plus delta, okay, is contained inside of Si. Okay? Now, since this could have been any Si, then that means, okay, so since x was in was anywhere in this union, okay, because I chose Si, I didn't choose a specific open set, okay, since for any x we pick inside of one of these open sets, okay, then that x is also going to be in the union, meaning that the union is still open, okay? So this implies that the union over all I and I of S sub I is open. And we draw a little box, okay? Unfortunately, this cute little theorem and proof are not going to stay on the board for long. Because, ladies and gentlemen, boys and girls who are watching, he says as if he wasn't a boy himself, okay, the moment you have all been waiting for has finally arrived. We are finally going to characterize or define continuity in terms of open sets. Here we go, ladies and gentlemen. Okay. How are we even going to do this? Our theorem states the following. First, let f from the reals to the reals be a function. Okay? Now, if f... sorry. I guess I gave you a little preview. First I have to define the preimage. Sorry. Okay. The preimage okay. What is the preimage? Well, the preimage is denoted like this. Preimage of S under F is equal to the set of all x in the domain. So this function goes from some domain to some codomain, such that f of x equals S. Okay? And S is just some subset of the codomain. Okay? So basically it's all of the elements x which map onto S via F. Okay? Nothing too crazy. Anyway, sorry. I'm just too excited to move on to this theorem, which is what the whole video has been leading up to. Okay? Let f from the reals to the reals be a function. Okay? So let it be a function. And now, if f is continuous, okay, then the preimage of S under F is open if is open whenever S is an open subset of the reals and vice versa. So if the preimage of S under F is open whenever S is an open subset of the reals, okay, then F is continuous. Whew. Gosh, man, I got tired writing the theorem. Whew, I'm psyched up. I love that sound. Okay, what's the proof of this theorem? Okay, so first we'll suppose that F is continuous. And if F is continuous, then recall the definition. Whoops. Then the open interval. Oh yeah. Then X is an element. So yeah, okay. X is an element of the open interval. Then for some A in the real numbers, X is an element of the open interval between A minus delta and A plus delta, therefore implying that F of X is an element of the open interval about F of A minus epsilon F of A plus epsilon. And remember that that delta and epsilon are both greater than 0. Okay? Now, to show, what do we want to show? That the preimage of S is open. Then, to show that the preimage of S is open, pick some A in the preimage of S. Okay? If it's open, then for some delta greater than 0. Okay? What happens? Remember the definition. The open interval about A minus delta, A plus delta, is completely contained inside of the preimage of S under F. Okay? Now, if this is true, then that looked like a smiley face for a second there. Then F of A is in S. Okay? And because S is open, okay? Because S is open, remember, S is an open subset of the real numbers. Okay? Then there exists an epsilon greater than 0 such that the open interval about F of A minus epsilon F of A plus epsilon. Oh, I just love this. Okay, is completely contained inside of S. Okay? This follows right from the definition of the open set. Okay? And now, what shall we do? Okay? Remember that if f is continuous, okay, then, okay, the open interval about f of a minus epsilon, then, x is an element of, x is an element of the open interval between, a minus delta to a plus delta, whenever, oh my goodness, which implies f of x, of course I don't have enough space, which implies f of x is in the open interval, oh my goodness, is in the open interval about f of a minus epsilon and f of a plus epsilon. Okay? But that looks awfully familiar. That's contained inside of S. So, okay, this is heating up. F of x is an element of that, which is contained inside S. So f of x, is contained inside of S, which therefore implies that x is contained inside of the pre-image of S under X. But look, X is in that. So, perfect. This all works out perfectly. This open interval is contained in the pre-image of S, and hence it's open. You thought we were done, didn't you? Now suppose that the opposite is true. The second part of the theorem, if the preimage of S under F is open whenever S is open, then does that imply that F is continuous? Okay, so let's suppose that the preimage of S under F is open whenever whenever S is open. Okay? What does this mean? Well, this means that we can choose any delta greater than 0 and any A, for example. We can choose, let A be in the domain of F and epsilon be in the real numbers. Okay? What does this mean? This means that the open interval about f of a minus epsilon, f of a plus epsilon is open. Yes, okay, so, well, okay, the reason we want to know this is because within this interval, okay, f of a is contained inside of this interval. So when we take the pre-image, okay, then A will be contained inside of the pre-image. Okay? So if this is open, which it is, then the preimage of it, then the open interval between a and x, a minus epsilon to a plus epsilon, is contained inside the preimage. Okay, so to conclude, okay, here we go. If x is in this open interval between a minus epsilon to a plus epsilon, that is contained inside of the preimage of the open interval between f of a minus epsilon to f of a plus epsilon, okay, which means that f of x, okay, is an element of this, okay, we applied f on both sides, the open interval between f of a minus epsilon, f of a plus epsilon, and now we can see from the definition that this implies that f is continuous, and we even had enough space to draw our box. This was a bit of a blockbuster crash course on continuity and open sets and how to link them via this theorem. This is going to be very useful, and I think this is a good place to restart my series on topology. Thank you for watching.